Hey everybody, so today we're going to be looking at calculating equilibrium constant. So really we're looking at when things reach equilibrium, what are the concentrations of the products and reactants we'll be working with here? Generally, the generic form of it is right up here, just kind of that. If you have a certain number of A molecules plus a certain number of B molecules in a reversible reaction, represented by this double-headed arrow here, you're going to end up with a certain number of moles of C molecules plus a certain number of moles of D molecules. And really, to find that equilibrium constant, what we would do is we're going to take the molarity, the concentration of substance C, raised to the power of whatever its coefficient is, okay? Times the molarity of D, raised to the power of however many molecules there are of it, over the molarity of A to the A power times the molarity of B to the B power. That, not that very useful. I mean, we can kind of see where the numbers kind of plug in, stuff like that. But let's actually use a real equation to figure out what this looks like. So the equation we're going to be looking at is nitrogen monoxide, 2NO, which is a gas, reacts with 2H2, 2 molecules of hydrogen gas, H2. It's a reversible reaction. Really, though, we're going to consider the products to be nitrogen gas, N2, which is a gas, and 2 molecules. Let's see if I can fix that quick. There it is. 2 molecules of H2O. In this case, we're looking at steam or water vapor, stuff like that. So if I want to make this equation look like this here, so I'm still going to say KEQ. I can make a better K than that. Good enough. So really the big thing though is we're taking the concentrations of the products, dividing it by the concentration of the reactants. So really what we're going to be looking at here is, let's say N2 is my C, H2O is my D, because those are my 2 products. And for the reactants, we're going to say that one's my A and that one's my B. So products over reactants. So the concentration of N2, and I can just do that just by going brackets N2. Now N2 doesn't have a number in front of it, so it's implied it's a 1. So it's implied there's a 1 there, and anything raised to the 1 power is itself. That's times the concentration of H2O. But for the H2O, there's a 2 in front of it. So that means that whatever that concentration of H2O is, raising it to the 2nd power. And that's going to be over the concentration of NO. Oh, got away from me there. And that's also raised to the 2nd power. Times the concentration of H2 raised to the 2nd power as well. All right, so really if we had some numbers to plug in here, this would tell us exactly what math we'd have to do to figure this out. So in this case, let's actually say that the concentration of N2, or of NO, is equal to, experimentally, we found out at equilibrium, doesn't matter what we started with, we have 0.62 molar of the nitrogen monoxide. We have 0.012 molar of the H2. For the products, we're looking at, oh, that was pretty bad. All right, 0.019 molar of the N2. And for the H2O, we're looking at, this one's pretty big, 0.138. Those are all molar. In the future, when I give a concentration in brackets like that, it's implied it's molar, so I won't be putting the M there anymore. All right, so we have numbers now. I know exactly where to put them. I've already figured out where my exponents are by looking at the chemical formula up there. So now I just need to plug these things in. So the KEQ is going to be equal to the concentration of N2, so 0.19 times the concentration of the H2O, but I have to square that one. So I'm going to put the square sign up there. And just make sure I get my PEMDAS right. Let's put parentheses there. That's over the concentration of the NO. So 0.062. That's also raised to the second power. We better parenthesize the bottom as well. Times the concentration of the H2, which is 0.012. That one's also squared. All right, extend this guy out. All right, so I know the math I need to do. Now I just need to actually grab a calculator and plug this stuff in. So I have 0.019. Oh, nope. There's my C. Haha, found you. So let's go parentheses 0.019 times 0.138. Hit the squared button there. Closing parentheses divided by opening parentheses 0.062 squared times 0.012, square that as well, closing parentheses, equals 653.7. That doesn't seem right. So that would be the equilibrium constant. Actually, let me go ahead and double check that with a calculator quick. Because that seems really ridiculously high. All right. 0.019. See, I don't have an easy square button. No. Sorry about that. We're going to go here, squared times 0.138. Oh, actually, that first one's not squared. That one is closing parentheses divided by open parentheses 0.062 squared times 0.012 squared closing parentheses. Yeah, I guess that's right. All right, so I double checked it. That math is correct there. So that's our KEQ, and that's really important because it doesn't matter how we change these things. We can always predict how some of the others are going to change. So for instance, so looking at that KEQ, let's say in this case, so kind of a new problem, so let me draw a line there. We're still working with this equation here, that reaction, which has this equilibrium constant. We're not going to change the temp of what we're looking at. But in this case, let's say we're going to change some things up so that the concentration of NO is equal to 0.1 and the concentration of H2 is equal to 0.01. Concentration of N2, let's say in this case we are making nitrogen gas, we're making N2. We want to know how much N2 there will be when the concentrations of the other three are here. So if we add, doesn't matter what we started with, if we end up with these three values here, we want to know what the value of the N2 is. Luckily for us, we already found the equilibrium constant, so I'm actually going to even keep that down here as well. So 653.7. Now that equilibrium constant actually tells me quite a bit too. It tells me since that number is way above 1, we're going to have way more of our products than we have reactants. And even when we look at the values they got, like 0.062, 0.012, those are the reactants. Products, we had 0.019 for the nitrogen gas. That's not a whole lot. But that is a lot of water that was made, a lot of H2O. And so we can kind of see how we had way more on top than what we had on the bottom. So we changed some numbers around, and we want to figure out how much N2 do we have. So still even looking like this is just going to be basic algebra here. So the KEQ, we said, was 653.7. We're going to set that equal to the concentration of the N2, which is what I'm looking for. And I'm even just going to leave that concentration of N2 times the concentration of the H2O squared. So let's not do that. So the concentration of the H2O we said was 0.4. We're going to square that number. And that's over the concentration of the NO squared. So 0.1 squared times the concentration of the H2, 0.01. And we're squaring that number as well. All right, parentheses around that stuff. You can do your squaring first if you want. I think we'll be okay if we wait until later. The big thing, though, is we're pretty much just doing algebra to get N2 by itself. So the first thing we're going to have to do is multiply both sides by this 0.1 squared times 0.01 squared, just to make sure that we're getting that out of the denominator. So we're going to have 653.7 times parentheses 0.1 squared times 0.01 squared. And that's going to equal the concentration of N2 times 0.4 squared. All right, N2 still not by itself. The next thing we'd have to do is just divide both sides by 0.4 squared. That cancels that. And over here, divided by just 0.4 squared. All right, don't have to worry about parentheses too much with this one. And I have N2 by itself now, so now I just need to grab the calculator, and I will trust it this time. Hit the C, so we have 653.7 times 0.1 squared times 0.01 squared, and that'll be divided by 0.4 squared. Plug that all in, and we should end up with a concentration of N2 of 0.004. Sounds good to me. And that'll be molar. Double check out the right number. 0.004. Yep, that'll do it. So right here. So equilibrium constant's kind of useful for two reasons. Number one, as we can see on the top there, it's good for figuring out whether we're going to have more products or reactants. You know, we can figure out what the equilibrium constant is. Greater than 1, more products. Less than 1, more reactants. The other thing is, once we know the equilibrium constant, we can actually calculate how much of these materials we're going to have. You know, based on the concentrations of all but one of them. We can calculate the last one. The math is pretty easy. I know my explanation wasn't all that straightforward, but the math is pretty easy. You just got to plug some stuff in. This is the first, and I think only time we're going to have to worry about exponents too much in here. But that's how you do it. All right, so with that, I'll let you guys go ahead and practice that in class. Good luck.